Let's talk about the last question on this final exam, which is question 13. So now we're doing a virtual math B homework, and instead of calculating this integral by hand or by calculator or by any Math 1B cheat trick, we're actually going to calculate this integral by a circuit instead, by having to build it and design it ourselves. Which is, to be honest, quite a good practice, I guess. So let's try to design a circuit such that the output of the circuit is this equation, is modeled by this equation. We have the following resources to use. We have a lot of wires, and then we have this current source being parallel with a 1F capacitor. We also have 2 op-amps, and then we have 2 resistors, and maybe we can build some kind of amplifier with these 2 resistors given that we have an op-amp. So let's try to observe the shape of this equation first. This has to be the output of our circuit. Well, fortunately, there are some circuit elements whose voltage across them can be modeled by an integral, and that will be for a capacitor. So, for example, the current across a capacitor is equal to the capacitance of that capacitor times the voltage across that capacitor's rate of change with respect to time. Which means the voltage across that capacitor can be modeled as an integral that is equal to 1 over c times the integral from 0 to the time that has passed, which I will note as tau here, and then times IC of t dt. The negative 1/5 here is a bit harder because we need a circuit or some kind of part of the circuit that can make the output a negative version of the input. That is what we do with an inverting amplifier, which takes 2 resistors and an op-amp. So let's try to design the circuit. So first of all, I need a capacitor block here. Such that I can first generate some kind of integral output. And I'll connect this to the positive terminal of one of the op-amps with a negative node directly linking to its output. So now I have made a unit buffer here, such that whatever I'm going to connect to the op-amp next, I will not be influencing the capacitor block. So to use an inverting setup, the input voltage has to be connected to the negative terminal. Since we don't have a reference for a virtual ground here, our positive node can just be 0. And then I'm going to connect the input to an inverting setup. Such that at last I have this Vout terminal here. Then now we just have to solve the concrete parts for the capacitor blocks and the inverter. So first, for the capacitor block, there's actually only one choice for us to put, which is the parallel of a current source whose whose amount of current outputted happens to be modeled after the function x equals t that we have to compute, and this being parallel to a capacitor of 1 farad. I'm going to connect this to the positive input, and the negative input can just be grounded, or maybe I can just make it an open circuit here. And so the voltage across the capacitor would be equal to 1 over 1 farad times the integral from the time from 0 to the time passed of x of t dt. And I know that the input voltage at V minus of the later op-amp must be equal to this current input voltage at the positive terminal of the front op-amp because of the unit buffer I have here. So now I just have to worry about the inverting setup. An inverting amplifier should look something like this. oops, meant to write something that takes a bit more space, such as this. All right. This is probably a clearer configuration to see. So let's say that we will name our resistors on the inverting op-amp R1 and R2. The gain of this inverting op-amp, or inverting amplifier, to be more specific and accurate, would be that Vout is equal to Vin times negative R2 over R1. And this should be also equal to negative 1/5 times the integral from 0 to tau x of t dt, and that happens to directly be Vn due to our capacitor circuit's work. So therefore, we'll actually need that R1 is equal to 5R2. So here we have two choices for the resistor setup. If we set R1 to be R fixed, then R2 will be equal to 200 ohms. If instead we have R2 be equal to R fixed, then R1 will be equal to R2 times 5, which will be 5k ohms. So both setups work since this R extra can have any possible resistance value that we want. It's just which one do we choose. And either way, this circuit configuration will work out such that Vout is equal to the integral equation that we try to solve here. And thus, by creating and having formulated the circuit model, we have solved the question.